we're going to continue chapter 5, which is the dimensional analysis, which we started on the Friday before reading week. And where we're going to go here is, first of all, look at what is the fundamental approach, Buckingham pi theorem. And it provides a way of sort of looking at a whole bunch of variables that you have identified. And I'll primarily do this with examples, but just sort of a process step. And you identify the number of dimensionless pi groups. So you list and count all the variables, n, and you list the dimensions of each of the variables. And again, up to you. But if you have looked at the updated crib sheet that I just posted yesterday, you'll notice that on each of the variables I've also listed all of the FLT and MLT, so force, length, and time, and mass, length, and time terms. So that's kind of helpful for this. But find J, the number of fundamental dimensions, usually 3 for MLT. That's where we usually go with all of this stuff. Sometimes we have theta, which is associated with temperature. Select repeating variables that are dimensionally independent, and then form the number of pi groups out of that, so n minus j. From that, write the final dimensions. Pi 1 equals a function of pi 2 and pi 3. And the other thing that you'll notice on that aid sheet is that there is a set of standard non-dimensional groups. So we have, as a startup, a function, force, length, velocity, rho, density, and viscosity. And again, as much as possible before the midterm next week on Wednesday, please take a look at the aid sheet. It really, it will help you with your studying, I hope, and that's one of the intentions of releasing it. Okay, so we have F, L, V, rho, and mu, and that gives us n equals to 5. And as you're supposed to do, you can then put in all of the dimensional terms. Yeah, there we go. So if you look at that, okay. So force, length, velocity, density, and viscosity. And again, I probably should have brought the aid sheet with me. You can take force. If you do an FLT system, it works really nicely for the force term, but the other terms get a little bit, well, mu and rho become a little bit painful. So you have force, you have length, you have velocity, and for force you have MLT to the minus 2. For length, it's length. Velocity, length over time. Density, you have mass over volume, so length cubed. And finally, for viscosity, you have mass over length and time. So I have J equals to 3 because I have M, L, and T. And so that is pi groups K equals N minus J, which equals 5 minus 3, which equals 2. And this is kind of remarkable that this works as well as it does. But that's all I have. So the number of pi groups I expect to get out of this is 2 pi groups. And they're going to be based on all of these. And I need to make some sort of choice here. And what I want is probably length, velocity, and density. So anytime I have a, sorry. N equals 5. N equals 5. My handwriting doesn't get any better. So you have 5 variables: force, length, velocity, rho, and mu. And one of the things I know from experience is that I expect to see a Reynolds number. I haven't done anything. Some of that is going to come when you do this a couple times. But these are not more than that. And let's just see. So I have pi 1, which is equal to length to the power a, velocity to the power b, mu to the power c, and force to the power 1, which is going to be LA LT minus 1 B ML minus 3 C MLT minus 2. So I want, for a dimensionless group, that each of those terms go to 0. So I have to split them up, L, M, and T. So MLT is all have to end up with powers of 0. So I'm going to combine them with the force, and this is so I have M, which is going to be C plus 1 is equal to 0. I have T, or L, I can do L, A plus B plus minus 3C plus 1 equals 0, and T, which is B minus 2 equals 0. So if I combine them, I see immediately that A, or C, is equal to minus 1, B is equal to 2, and then I can substitute all the terms in. And so pi 1 is equal to L to the minus 2, V to the minus 2, and rho to the minus 1, and F, which yields a pi 1, which is equal to F rho V squared over L squared, which is equal to a coefficient of friction. And again, as much as you go through all of this exercise and you calculate each of these terms, what you should do separately is make sure that they kind of match up with an existing pi group or a non-dimensional group. And that non-dimensional group, I'll show you a whole list of them after. So pi 2, I'm going to put that with mu. LA, VB, rho C, mu to the minus 1. So I'm cheating a little bit here. Yeah.
You got like mu to this exponential c, but how you got rho to the exponential minus 1, like before that? Like,
Which one?
how you go from mu to rho?
So I've done all of the additions over here. So all of the terms have to equal 0. So all of the m terms are separated out. So I have m to the minus 3c, and I have m to the minus 2. Or no, m to 1. or m to the c, m to the minus, or m, it's c plus 1. Sorry.
But like, I don't really understand how you, like the original equation, there isn't any rho here, but there's a mu here. But how you get a rho result?
Which term do I have a rho?
So in the first equation you have L, mu, rho, and M, right?
No, LV mu.
Mu and M. And then after that you have your I1 equals L, mu, rho, M.
Where? So each of the terms, I've taken the, maybe we go back a step here. So I have different variables. So I've taken these as my repeating variables. Oh, wait a minute. Did I change this? No. Sorry. That should be rho. Okay, sorry. When I read these things, I read them quickly. So again, same thing over here. And again, what I'm trying to do is I've taken, in the first one I have f, in the second one I have mu, and I already know what I'm going to get. I'm going to get Reynolds number. If I'm going to get Reynolds number, then what will happen is that the mu, in this case, if I set it to 1, will be on top. So I don't want to have it on top. I want it on the bottom. So I set it to -1 to start. And if I do that, I'll solve for A equals to 1, B equals to 1, C equals to 1. And then pi 2 is just going to be rho V L over mu. And that equals a Reynolds number. So as a Reynolds number, anytime I have anything that's moving, I kind of expect to have a Reynolds number as part of it. So the next 2 chapters, when we start to talk about things, we'll talk about pipe flows and external flows, and Reynolds numbers will appear very frequently. So you expect to have a Reynolds number in all of your results, usually if you have a velocity. Any questions so far on this one? Let's do another one. So more terms. So in this case, we have a centrifugal pump. We want to know what the power is. And the power is a function of flow rate, diameter, rotation rate, omega, density, and viscosity. And so we have a function that goes as power equals QD, omega, rho, and mu. And we're going to do the same thing again. And here what we're going to see, and use an FLT system. I hate them. But that's one of the things that with lectures you have to do it this way. You have more options on your own. So I have P, Q, D, omega, rho, and mu. And that will give me an n equals to 6. I've been forced to use an FLT system. So J equals 3. And I get K equals n minus J, which is equal to 3. So unlike the previous problem, because I have this extra variable in there, I will have 3 pi groups that appear. But again, I'm trying to make sure that as I go through and I look at that list that I eventually will show you of the various types of constants that we look at. K equals n minus G, and we will choose as our repeating variables D, Q, or no, not Q, omega, and rho. So the real problem here in all of this is this step, where I say, hey, look, this is the best set of repeating variables to use, because those are not always going to be intuitive. And again, that chart looking at the different types of dimensionless groups will be very helpful in sort of guiding your decisions with this. But again, I've kind of tried to keep everything so I have something that's rotating and it's got a speed. I'm expecting, and you have the answer here. You have the Reynolds number and then a coefficient of mass flow or volume flow. So I'll end up with Cp, which equals power over rho So again, I end up with a set of variables out of this, and if you do the calculations, which you should, you'll end up with C sub P, C sub Q, Reynolds number, and you can kind of do a really quick check on some of this. You know, omega is going to be inverse seconds, and that will sort of, rotation rate. D to the fifth, you have diameter, you have power on the top, and the really tricky bit in this is not the obvious one. This one kind of works really well. 1 over seconds times meters cubed equals meters cubed per second, so it is dimensionless. Power is not, I don't remember what power is in terms of MLT or FLT systems. I look at a table. Reynolds number, same sort of thing. I've got here a different form of it, but it basically is velocity times diameter over rho, or times rho divided by mu. So it is a Reynolds number in the same sense. It's just going to take a different form because I have a flow rate associated with it, or a volumetric flow rate, not a velocity. I could set this up and write it out as velocity and mass flow, but why? It works the same way. I just want to see where I am. I actually want to skip this one. Okay, there's another approach to this. And the other approach is to use Ipsen's approach. There's no counting required. There's no pre-selection of the repeating variables. It can be systematic and foolproof as long as you know what you're doing. And again, there's a lot of experience / intuition that goes into this. It is helpful to know what it is and to recognize that you can use it as a way of sort of solving these problems. So if I go back to the first one, where I had force as a function of rho, L, mu, and, okay, L, V, rho, mu. So force, some sort of length scale, velocity scale, density, and viscosity. And I put all of this together, I can just say this is MLT to the minus 2. And this is LT to the minus 1, ML minus 3, M over LT. So I've written all of the same terms, and what I want to do is start to combine them and try to get rid of any expressions that I have somehow. So what I want to do first is eliminate the mass. So that's straightforward because in the previous slide, I only had mass here. Well, I have mass here and here. But I can divide that out by rho across each of these terms. So if I take it here, divide by rho, and divide by rho, then I have eliminated it by writing this as, oops, and not what I wanted. Force over density is equal to a function of L V mu over rho. So this, all the terms that have mass in it, I have now canceled it out. So if I divide by rho, I get one term. If I want to eliminate time, I can do that by doing rho v squared equals a function of length and mu over rho v. And again, at this point, I have eliminated mass and I have eliminated time. The only term left is length, and I can do that by sort of dividing out. Now I'll end up with an inverted Reynolds number. So I end up with rho v squared L squared equals a function of mu over rho v L. Now the only disadvantage, of course, is that that's an inverted Reynolds number. But that's not serious. This is not quantitative analysis. So I can write this as C sub f is equal to a function of Reynolds number. Same result. My preference, honestly, is to use the pi theorem. It's a lot easier to use, and it surprisingly requires less sort of intuition. But if you got something that is kind of close to what you want, then it's okay. Any questions so far? Go ahead.
Will we ever be asked to do the ISPIN method specifically, or will we be always given the option to do the Buckingham or ISPIN?
No, you would have the option to do it the way you want to. I just have to check and make sure that I have not done that. Okay. So yeah, no, that's not a fair. It's not fair to expect you to do it one way or the other. And even if you did it, okay, even if we required you for some strange reason to use the Ibsen's method, you could play a game where you solve it with the Buckingham pi theorem and then write, okay, here's all of the answers, doing the divide by L, divide by T, divide, whatever. And so the result would be the same, and it's a good way to check. So the way to use this, I think, is to check the result.
Let's say you have two pi groups, right? How would you know that what you have is either the Reynolds number or the sum of the coefficients?
Sorry, go ahead again.
If you have two or more pi groups, how would you know that the arrangement of the variables that you put in is going to be the Reynolds number or the sum of the coefficients?
So, okay, this is where the intuition bit gets in, and that's where I get a little bit hesitant. So every time you have anything that involves a velocity, you expect to have a Reynolds number at the end. If you have a force, you expect to have a drag force coefficient. You expect to have a force coefficient of some sort. Every time you do this, you kind of have to refer back. And what I'm trying to do desperately is, because I know I have a chart here. And I just want to know where I put it. Oh. And knowing me, I put it right at the very end today. Okay, so if you look at what is marked as slide 68, I put 68 and 69. I do list all of the terms that you need. So, sorry. so to answer your question, if you have a velocity, if you have a force, you know that you're going to end up with standard dimensional groups. Those standard dimensional groups, you should have a list of them. So if you look at the current aid sheet, I think I put down all of the standard ones that are useful to you. And from that, you also use that as a guide. So the intuition is there, but really it's just dividing things out. The Ipsen method might be a little bit better in some ways, but I really think the pi approach is much better in the end. Do I want to skip this one? I'm just looking at the time and how enthusiastic I want to be. Okay. All right. This is the first year I'm trying these notes. That's why I want to sort of be reasonable and cover what I want, but not go crazy. All right, so just as a repeat of what we did, you have the Buckingham pi theorem. This is all it is. But in summary, if a process involves n variables, m fundamental dimensions, the relationship between the variables can be expressed as k dimensionless pi groups. And that's where you're going to with k equals n minus m. And it's pi 1 equals a function of pi 2. And usually you can choose reasonably well how to do all of these terms. You'll end up with strange groups, but you have to check your dimensional analysis. So one of the things that you have been harped on for years and years, is to make sure that you do unit calculations. This is an application of unit calculations. So even if you make an error in, say, not choosing the ones that, for example, I might have chosen, but your dimensional groups are still dimensionless, that's the correct answer. It's not always the optimal answer, but there you go. Sorry. Oh, weird. Okay, so repeating variables, simple. Construct pi groups. You select m repeating variables of the original n variables. The set of repeating variables collectively contain all m fundamental dimensions. So MLT usually. Again, the decision is yours. I would not ever do anything with FLT unless I was forced to. They should not form a dimensionless group by themselves. It's best to choose fundamental variables, length, velocity, and density. So if you choose length, you got length. Velocity, you got time. And density, you have mass. And those are all unique to each other. And that's kind of a helpful way to start out all of these things. So you don't want to have something like viscosity because it's going to sort of combine with everything and kind of make things worse. List variables and dimensions. So identify all relevant variables in the problem and calculate or identify all of the base units, m, and then get the number of fundamental pi groups. So k equals n minus m. Select the pi groups, and then you just write it out as non-repeating variables with the repeating variables. You solve for the exponents for each pi group. Solve for each of the exponents for each of the pi groups. Substitute the dimensions and solve for the exponents by ensuring the group is dimensionless the net power or the net power of m, l, and t is 0, and then everything works out well. So again, that one step where you choose your repeating variables is the really important step. Everything else sort of works out reasonably well. Express the final result as a relationship between the derived pi groups, typically with the pi groups containing the dimensional variable on the left-hand side. So we could do this again, and it's kind of useful to do this. We have n equals 5 terms here, where force of drag you have m, l, t to the minus 2. So on a smooth sphere, you're going to identify your diameter as important. Velocity is Lt minus 1. And rho is ml minus 3. You have mu ml minus 1, or yeah, t minus 1. So same groups of variables. You're using MLT. So K is n minus 5, or m, which yields 5 minus 3, which equals 2. So repeating variables, density, because I have a mass term in there, and velocity, because I have a time term in there, and length, or diameter. And my non-repeating variables combine mass, length, and time, so force of drag and viscosity. So all I'm doing, again, same sort of thing, but I'm going to approach it a little bit differently in terms of trying to solve it. So again, same kind of thing, but now we're looking at force of drag, so spheres, you have a lot of work done in that. If you go through the album Flow Visualization, you can see flow past the sphere. It's actually kind of fascinating to see some of these results. If you write it out, you can write m, which is A1 plus B0 plus C0 plus 1 equals 0. L is A to the minus 3 plus B to the 1 plus C1 plus 1 equals 0. And time is A0 plus B minus 1 plus C0 minus 2 equals 0. So you have a matrix you can solve. And if you solve through for that matrix, you get the same sort of results as before. But they're different in the sense that now my pi1 group is for drag force. So this is for pi1, and I'm using as my repeating variable force of drag. Should mention that. There are ways to solve this so that you don't spend a great deal of effort. Again, each of the approaches in the end are relatively straightforward. You know, A equals minus 1 is pretty obvious here. B equals minus 2 is also obvious because the other two terms go to 0. You divide by negative 1, and then you kind of put it through. Minus B equals 2. Minus 2. Oh. Okay. Oops. So if we do the same thing here, again, as already before I started this problem, I know it's going to be a Reynolds number because I have density, viscosity. In fact, I'd probably write this as kinematic viscosity and avoid some of this, but there you go. Velocity and diameter, and I end up with m a to the 1 plus b 0 plus c 0 plus 1 equals 0, L a to the minus 3 plus b to the 1 plus c 1 minus 1 equals 0. Time is a 0, b minus 1 plus c 0 minus 1 equals 0. And I end up with a equals minus 1, b equals minus 1, c equals minus 1. And I end up with pi 2, which is mu over rho Vd. And so that's the Reynolds number, again, inverted, because I didn't define this as a negative 1 to start. Same sort of results. Any questions so far? The operation is straightforward. It really is putting everything together and organizing it correctly that is challenging. So you can also solve this as 1, 0, 0, minus 3, 1, 1, 0, minus 1, 0, A, B, and C, which equals minus 1, 2. And for the second one, 1, 0, 0, minus 3, 1, 1, 0, minus 1, 0, A, B, and C, which is minus 1, 1, and 1. These end up with the same result. No surprises there. So you end up with drag coefficient and Reynolds number. And any time that I have something that says inverse Reynolds number, I'm going to flip it. And again, you're allowed to do this because you are not doing quantitative math here. You're not doing any type of calculation. You're just showing that there is a relationship between one set of variables and another. So even though you get an inverse relationship for Reynolds number, you can just say C sub d is a function of Reynolds number. And if you look, when we go into chapter 7 and we start to look at flow past spheres, flow past an obstacle, we're going to see lots of different cases of that. Questions? So it's really just a lot of different ways of solving the same problem and recognizing where these terms are. So when it comes to dimensional analysis, it's a powerful tool for reducing complexity of physical problems, and this is where we use it mostly. Principal dimensional homogeneity, or just simply unit calculations, which you have done for years and years so far. is really important to this, and it helps guide you in terms of making choices and making the right choices as you're going through all of these problems. Buckingham pi theorem, honestly, it's probably the easiest of all of the stuff I showed you today. There are different ways to approach this, but frankly, I would use the Buckingham pi theorem in almost all of the cases that I did. Choice of scaling, repeating variable is up to the user and affects, and this is where it gets hard. To be honest, the intuition, I can do this because I've done it for a number of years. The first time I saw it, it was really hard, because how do you choose? But basically, all you do is you say, hey, I've got a mass term here, I've got a length term here, and I've got a time term here, and they're independent of each other. There's no mix of mass and time, there's no mix, and then I can use that. I do that with the length, so I mean, it's kind of difficult to avoid that. Similarity and scaling laws, which are crucial for model testing and engineering, and we'll talk in the next lecture about those. So just a shout back to chapter 4, which is kind of useful. We can always non-dimensionalize equations. So I do a lot of experiments, and my students do a lot of experiments. And we tend to take the equations of motion and we say, okay, we have continuity, we have momentum, Navier-Stokes equation, and we start there, and we can define characteristic scales for the problem. Say a reference velocity or a length, rewrite all of the variables and equations in terms of these scales, identify the dimensionless parameters that emerge as coefficients in the equation. So what you should not be surprised at is your favorite number, my favorite number, Reynolds number appears in a lot. So if we take that sort of approach, we can say V star is equal to V over U, which is a characteristic velocity, X over L, which is a characteristic length. Time we have to do a little bit more with. So time, what we do is we divide length and multiply by velocity. So if you've got meters per second divided by a length, you have inverse seconds. So that term, T star, actually ends up being non-dimensional. And the most painful problem is pressure, which is pressure plus rho g z over rho u n. Rho u squared. And what we end up with is if we substitute back in, we have delta star, so the gradient of velocity, and this again is assuming incompressible flow, steady state, and we end up with inverse delta star, gradient, inverse gradient. There we go. Where more interesting I end up with a Reynolds number. Now, in all of these cases, especially as mechanical engineers, we always deal with really velocities. These are non-dimensionalized acceleration, non-dimensionalized pressure, gradient, and here I have 1 over Reynolds number based on some sort of length scale. So all those terms come out, and it kind of works really well. So, from the momentum equation, we always have Reynolds number, rho UL over mu, and what you start to think about these things are to relate them not to not to non-dimensional numbers that don't have physical meaning, but to ratios. So you have inertial forces over viscous forces. For boundary conditions, you have pressure forces over inertial forces. Inertial forces are associated with kinetic energy or anything to do with velocity. Froude number, generally free surface flows, you have u squared over gl. Weber number for small flows, so if you're looking at the surface, a meniscus of a droplet or something of that nature, and again, ratio of inertial forces to surface tension forces. So you have all of these relationships that kind of relate how fast things are going. So one of the things that we do with this equation at the bottom is say, hey, I can get rid of a lot of terms, say, for example, viscosity, this last term, because it's associated with viscosity, if this is very high. So very high Reynolds number is associated with potential flows. And you end up not doing it in this course, but in other courses. In very specific cases, we have Mach number, so very high speed flows, and it's flow speed over speed of sound. You also have specific heat ratio, Struhal number. So I do, again, my background, I'm doing a lot of work looking at aerodynamic control, and we look at flow past wings. And one of the important parameters is Struhal number, which is the vortex shedding off of a wing as flow goes by. So you have a flow, and what you see, and this is over years of experiments, not just mine, but many, is rotating regions of fluid. I probably should go the other way. Rotating regions of fluid that sort of shed off an airfoil and are identifiable. So we do that for vortex shedding. And finally, roughness ratio. So on Friday, we'll start to look at roughness ratio when we look at pipes. And within pipes, they're very important for a parameter called the Moody diagram, which will be your life for 6 or 7, 5, 6 lectures. So that's what vortex shedding looks like. So you have a flow. This is not, it's not a fixed object. It is the fluid, so here air, for example, going past a rectangular cylinder. And when I say rectangular cylinder, it's something like this. You have shedding off of, you have shedding that comes off. So if you've ever looked at, say, if you've ever been on a dock and you've watched the flow go past one of the legs of the dock, you'll have seen this phenomenon. So, oh, this is a circular cylinder, sorry. And this is the Struhal number versus Reynolds number. So, just to avoid problems. Yeah. So what you have is a wake, and as the wake develops, you have these alternating vortices that appear. Struhal number, and so one of the things that we've spent a lot of effort on, and this is a century, it's about a century, of looking at flow past cylinders, is identifying these regions. So these are your key dimensionless groups. This is kind of a physical meaning, and as you're doing your pi theorem, as you're analyzing all of these results, the really important thing is to understand they do have something, they mean something. So drag force over dynamic force, lift force over dynamic force, inertia over viscosity. All of these terms later on help you decide when you're doing an analysis what terms are important and what terms aren't. And at high Reynolds number, we generally try to drop off viscosity. And I think, okay, so we get a dictionary out of this. Let me just see if there's anything I really want to go through. This will be chapter 7.